In this lab, the purpose was to experimentally analyze projectile motion and compare it to computational predictions based on Newton's second law. The system is a Powerade bottle cap with a mass of 0.0013 kilograms. The surroundings include Earth, which provides the gravitational force, and the air, which provides a drag force. I constructed two computational models. The first model includes only gravity as the force acting on the cap. The second model includes both gravity and the quadratic air resistance proportional to velocity squared. The main result of the lab is that gravity-only model slightly overestimates the horizontal range and peak height, which includes air resistance, produces a trajectory that more closely matches the experimental data. The object was a Powerade bottle cap with a mass of 0.0013 kilograms. The camera was fixed and the motion remained in the plane of the screen. I placed a yardstick in the frame to calibrate distance and tracker. The x-axis was placed along the bottom of a whiteboard and the origin was set directly below the release point. I tracked the cap frame by frame to extract time, x position, and y position. The cap lands at approximately 0.767 seconds with a horizontal range of about 1.09 meters. My first model applies Newton's second law. The only force acting is gravity. Therefore, acceleration is constant and equal to negative g in the y direction. The second model adds quadratic air resistance. The drag force points opposite velocity and has a magnitude proportional to the speed squared. The constant b was tuned so that the predicted trajectory best matched the experimental data. So this graph compares all three trajectories. The gravitational only model is slightly overestimates in a bunch of places, like the range and the peak height. The drag model produces a slightly shorter range and better matches the experimental data. The major source of error is really the tracker precision and the calibration alignment, along with slight camera movement and distortion. As the time goes on, as the velocity increases, the frame rate affects how much of the Powerade bottle you can actually see, so it kind of is hard to exactly find the position. So, do any of my models predict a terminal velocity? No. Terminal velocity means the force balances, so net force is zero. So acceleration becomes zero and velocity becomes constant. In the gravity-only model, there's no terminal velocity because the only force is gravity. So the acceleration stays at negative g, the velocity keeps changing. In the drag model, terminal velocity can happen during a long vertical fall because drag increases with speed until its weight balances. In the projectile experiment, the cap doesn't fall long enough for V of t to level off clearly. So a similar experiment to find terminal velocity would be a drop, to drop the cap straight down from a much larger height, and then track V of y versus time, the tracker, and look for a section where the velocity becomes approximately constant, like a plateau, would be the terminal velocity. So what if the object was thrown straight up with the same magnitude of initial velocity? It would take longer to reach the ground if it was thrown up with the exact same initial speed, because my initial throw had computed, an x component of the velocity and a y component of the velocity. So the initial speed was, root v of x squared plus v of y squared, and that's equivalent to 3.67 meters per second. So for vertical motion, the height would be y of 0 plus v of 0 times time minus 1/2 gt squared. Setting y of t equal to 0 and solving gives me a landing time of about 0.82 seconds, which is longer than the original flat flight time of 0.767 seconds. That makes sense because in the straight-up case, all the initial speed contributes to the upwards motion, and the object spends extra time going up and coming back down versus traveling to the right. So, in conclusion, the gravity-only model slightly overestimates the trajectory and includes quadratic drag, improves agreement with the experimental data. So for the short flight, air resistance is present but relatively small compared to gravity. That's the end of my Lab 2 report. Thank you for watching.